All right, welcome everyone. In this lesson, we're going to be looking at the natural logarithm function. And so we've been talking about exponential functions and the natural exponential function in particular. And really the natural logarithm is related to that natural exponential function. And the way we define it is with this relationship. So the definition is that y is equal to the natural log of x, and we use ln to denote natural log, if and only if x is equal to e raised to the power y. So essentially we can think of the natural log as being the exponent from our exponential function. And really how we're gonna think of this logarithm is, so y equal to natural log x, it's really the inverse function of the natural exponential function. And that's and by inverse, what do we mean by inverse? It's kind of the key word there. So this word inverse. Well, the inverse of a function effectively undoes, or we can use it to kind of cancel whatever the other function does. So what we're going to see is that natural log and the exponential functions, they're inverse functions of each other. So natural log is going to cancel off whatever the e to the x function does, and the e to the x function is going to be able to cancel off whatever the natural log function does. So we're going to see that they're really inverse. They have a cancellation property. Now graphically, the way an inverse function looks is you take whatever kind of starting function. So in this case, we have our y equals e to the x, our exponential function here. And to see what the graph of its inverse function would look like, you reflect it across the line y equal to x. So what does that mean? Well, any point on the graph of y equal e to the x, to get the graph of the natural log function, it's going to have kind of a mirror image where we reflect it right through this diagonal line. And that's going to give us a point on our natural log curve. So for instance, we have this point 0, 1 on our exponential, and on our natural log function, we have the point 1, 0. So really, this is the graph here, and we could do that for every single point. So I could pick a point here and look at its mirror image, and we could just keep doing that over and over until we get the graph of what the natural log function looks like. And so here it is. So it's really a reflection of the curve y equals e to the x over this diagonal line y equals x. So we're doing a reflection across that line to see what the graph of our natural log function does. Now, there are some properties, so things that we've discussed before, and now we're gonna think about them in terms of the natural log function. So first of all, one of there's maybe two special points on our natural log function. So the first one is that the natural log of 1 is 0. And we can see that right here on our graph. That's where our natural log function crosses the x-axis. All right, well, what else do we know? Well, we know that our natural log function is only defined when x is greater than 0. So really this tells us that the domain of our function is the interval from 0 to infinity. So we can't plug negative numbers in. We can't even plug 0 into the natural log function. What else do we know by looking at this graph? Well, the natural log of x is less than 0 when x is in between 0 and 1. And we can see that right here along our graph. Let's use a... So we can see that right here, that our natural log ln x is negative on the interval 0 to 1. So you pick any number in between 0 and 1, and the natural log function would give you a negative value. And you can see that because on that section, it's below the x-axis. Now, similar, if we go to the other side of x equals 1, so remember, x equals 1 is where we cross the x-axis. To the left of that, we're negative, and then to the right of that, we're positive. So over on the other side, our natural log function is positive. So it's positive on that interval from 1 to infinity. What else do we see if we look at this graph? Well, as we read from left to right, the function's always going to be increasing. And we also see that it has that concave down bend to it. So the graph, as we read left to right, it's kind of bending down. It has that concave down bend. And really, you can think of that again as drawing a tangent line. And what you see is that at any point you draw the tangent line, the curve is going to fall below that tangent line. Even where it's not so obvious, you draw the tangent line, and the curve still, it's slightly bending below. So our function is increasing, but it's always concave down. And then some other properties that we're really going to be using, take advantage of, are these cancellation properties. And so if we have the exponential function with ln x up in the exponent, well, the e and the natural log effectively are going to cancel out, and they give us just x. And this is going to be true for any x greater than 0. And then same thing, going the other way, if we have natural log as our outer function and we plug e to the x into that outer function, well, again, the natural log and the e are going to cancel off, and we're just going to get x out. So these cancellation properties are going to be very helpful. And that last one works for any x. So x could be positive or x could be negative. All right, and maybe one other, just to mention, one other kind of important point or value here is that the natural log of e is equal to 1. So if we just plug the number e into the natural log function, we get 1. All right, so we're going to keep these in mind. But let's try an example where we get to use that cancellation property. So maybe let's keep those cancellation properties in view there. All right, so we want to simplify this equation. And what's or simplify this expression? And what's our expression? We have e, and then in the exponent we have natural log of 4 plus 2 times the natural log of 3. All right, so let's start by using what we know about just exponential functions in general. So we have an exponential rule. Let me just rewrite this, make it a little bigger. And we have an exponential rule that says if we have addition up in our exponent, well, we can split up that exponential function, that exponential term, based on that addition. and we could split it up into two exponential terms, and then it becomes multiplication. So the way this property looks, this is e raised to the a plus b is equal to e raised to the a times e raised to the power b. So this is our one exponential law that allows us, if we see addition, we can split it up into two separate exponential functions, and then it becomes multiplication. Okay. So now we can simplify one of these terms. So the first term here we can simplify. We can immediately cancel these off because the inner function is this natural log 4, and then our outer function is this e, and the e and the natural log are directly next to each other, so we can cancel those off. So let's use our cancellation property once. All right, now the issue is I can't do that here yet because this 2 is kind of getting in the way. So the cancellation property only works, if we go back up, when it's e and then immediately following it or inside of it is natural log of just some term. So this 2 is kind of stopping us. So we can use another exponent rule that essentially allows us to take this 2 and kind of factor it off. And we can write that as e raised to the natural log of 3, the whole thing squared. And this is another exponential rule that we're using here that says if we have e raised to some power a, and then that whole thing raised to another power b, well, what we can do is we can just multiply those terms, multiply those exponents together. Except now we're kind of doing that in reverse. So we had two exponents getting multiplied together here. So we had 2 and natural log of 3. So we had two numbers getting multiplied together. And as we're doing these, whenever you see a natural log of a number, don't be too worried. Think of it just like a fancy number. That's really what it is. So this natural log of 3, even though it looks complicated, it's just a number. So we have two numbers being multiplied here. And so what we can do when we have two numbers in our exponent term getting multiplied, well, we can kind of apply one of the exponents first and then put parentheses and then apply the other term second. And that's what we've done. Applying the natural log 3 term first, and then I put parentheses, and then we have the 2. And then once we're here, we're all good. The e and the natural log are right next to each other, so we can use our cancellation property. All right, so we got to use it twice here. Once here, and then once right here. And so once we do that, what are we going to have left? Well, we have our 4. There it is. And now inside the parentheses here, the e and the natural log are canceled, and then the only thing that's left is the 3. And the 3 kind of works its way down to the main level of our line here. So we're going to have 4 times 3 inside the parentheses, and then that whole thing squared. That whole term inside the parentheses squared. And if we finish that off, we get 4 times 9, which is 36. All right, so we are able to use some cancellation properties and then a few of our exponent laws. All right, let's try. So having this natural log function is really going to kind of improve our ability to solve equations involving exponential functions. And so in example 2, we're going to see kind of the main strategy for how to solve an exponential equation. And I call it an exponential equation because inside this equation, there's an exponential term and the exponent, where the variable is that we're trying to solve for, is up in the exponent. So we're going to see how to solve exponential equations for x. And the main strategy here is step one, we want to solve for the exponential term first. And then once we have the exponential term on one side and then everything else on the other side, we're going to apply natural log to both sides. And then once we do that, we're going to be able to use that cancellation property to kind of get the x out of the exponent. All right, so let's try this one out. So let's start by, well, let's write our equation. 5e to the x minus 3 minus 4 is equal to 0. So the issue here is that our variable that we're trying to solve for is up in the exponent. All right, so what we want to do is we want to isolate that exponential term. We want to get it all by itself. So what can we do? Well, we want to move this constant term to the other side of the equation. So I'm going to start by adding 4. And then we'll also want to get rid of this 5. We want the 5 off of the exponential term. So what I can do is I can first add 4 to both sides and then divide both sides by 5. All right, so once we're there, then the next step, so that's really step one. Get your exponential term all by itself on one side, and then anything that doesn't have the exponential term, move it over to the other side of the equation. Then step two is going to be, we're going to apply natural log to both sides. So we'll have natural log of e raised to the x minus 3. And then over on the other side, we'll have natural log of 4 over 5. And now, once we've done that, that's step two. Once we've done that, then we can use our cancellation property. So we're going to be able to cancel off the natural log and the e. So we're going to get our money's worth with this cancellation property. And then once we do that, over on the left side of our equation, we're still going to have that x minus 3 from our exponent, but now it's kind of on the main level of our equation here. So it's going to be x minus 3 is equal to natural log 4 over 5. And again, even though this looks complicated, just think of this as a fancy number. That's all it is. This is just a fancy number. And then finally, once we've done the cancellation property, there still might be some solving left to do. So in this case, there's a little bit. So we got a little solving left to do. And all we need is to add 3 to both sides. And that's going to give us x is equal to natural log 4 over 5 plus 3. All right, so we did it. And that cancellation property really came in helpful. Now this is for exponential function or exponential equations where the unknown variable that we're trying to solve for is up in the exponent. There is another type of equation, and that's a logarithmic equation. Kind of tricky to say. And for logarithmic equations, the unknown variable that we're trying to solve for is inside of a log function. And the idea is going to be the same. We want to solve for the logarithmic term. Then once we have that all by itself on one side of the equation, we're going to apply the exponential function to both sides. And then we'll use our cancellation. So it's just kind of the opposite because we're going to try to undo this natural log function to get the x out of it. All right, so let's see how this is going to look. So first, let me just write the equation. So 2 times natural log x plus 7 is equal to 0. And again, what we want to do is we want to isolate this natural log x term. So we want to move everything over to the other side of the equation. So subtract 7, and then once we get 7 over on the other side, then we can divide by 2 to get rid of that constant in front. And that's really step one. Get the natural log term where the x is all by itself. So we get natural log x is equal to negative 7 over 2. Once we have that, the next step is we want to get rid of the natural log. We want that out of there. So the way to get rid of the natural log is with our exponential function, and we're going to apply the natural the natural exponential function e to both sides. Now when we do that, each term each side of this equation is going to become the exponent. So it's going to be e raised to the natural log x is equal to e raised to the negative 7 over 2. So in this equation, these terms were all kind of like on the main level of the equation. And now once we apply the exponential function to both sides, those terms are now, they went upstairs. They're now in the exponent. And so as soon as we have that done, then we can use our cancellation property. E and natural log are going to cancel off like that. So again, we can use our cancellation. And then in this case, once we do that, we're good. We have x. So the only thing left on the left side of the equation here is the x. So x is equal to e raised to the negative 7 over 2. And that's our solution. So this cancellation property is going to be pretty helpful with kind of working with these exponential and logarithmic functions. So where we're going to go next with this is we're going to see, well, now we have a new function to consider. How do we differentiate it? And how do we do more complicated derivatives of it? So we'll see you then. Bye-bye.